Okay, so it's 10 o'clock. I will give you a few minutes to work on this little problem here. But just as a recap of what we've been doing, last class we learned the value iteration algorithm, which takes in, it's a way to solve equations that look like the Bellman equation. And so those are equations that look like x equals cosine of x. And the idea is you just apply the function, whatever it is on the right-hand side, you apply it over and over again. Last time we did it on the real Bellman equation for the game Pig. And we had, in Pig, you can either stay or roll again. So we had a Q function for staying, we had a Q function for rolling again. The nice thing about Pig is the stay function is very simple. If you choose to stay, we know exactly what score you're going to get. If you roll again, it's not so clear what the value is, right? And we found the answer by doing 8 iterations of the Bellman equation. And we came up with this final answer, which was the value function for staying and for rolling again, depending on what state you're in. And from that, we could read what is the optimal strategy. So if staying gives you more points than rolling again, then you should stay. So you stay up here. If rolling again gives you more points than staying, then you should roll again. So by calculating the Q values, which the quality of state-action pairs, so for every state and for both actions, staying and rolling again, we found the value of both. We found the optimal strategy in this game Pig, and it matches kind of what you would do by just using a pen and paper. That's what we did last time. And it was all from this value iteration algorithm, which I copied and pasted the little algorithm from the textbook. So this is the very famous reinforcement learning book by Sutton and Bartow. And this is their value iteration algorithm written as an algorithm. They are using the function v. So they say, let's do v of s. That's what we did as well. And here they have a little loop. They use this delta as a little trigger to say, let's stop the loop when we reach some threshold of things have not changed very much. And delta keeps track of how much things have changed. You could also loop for a fixed number of iterations. So when we did it, I just said, let's do 13 iterations. We could have also said, stop looping when the amount that it changes is less than 0.01. Then you would set that delta value to 0.01. It would be the same idea. But in the loop, what do you do? Well, you just, at every step, you make v of s the maximum value. And this thing looks very complicated, but this is the matrix M times the rewards plus the values. So that is our equation. That is this part of the equation. Let's write it out. Right. V of k plus 1 is the maximum over all actions A that are possible from state S of the rewards plus the matrix M of choosing the action A, getting VK. Okay. All of this at S. Okay. So this is the way we wrote it. So we were thinking in terms of matrices, because we have all taken a linear algebra course. We love linear algebra. Okay, we've all taken a linear algebra course. So we have the matrix M, and when we were just doing Markov chains, there was one matrix M, but now we're doing Markov decision processes, so there is a matrix M for every action, right? If you fix the action, then there's some probability you go to the next state. And so MAV is moving forward in time by one step, and this is the value iteration, the equation for the value iteration. This is the real Bellman equation we derived last time. Okay, so all of this is recap. Why am I saying this? Well, in the algorithm, it looks like they did it differently. But it's actually the same thing. It's the maximum. They wrote out the sum. So we wrote matrix. They wrote out sum. But it's the same thing. And that updates V from what it was before to the new V. And then they keep track of how much has it changed. And if it hasn't changed too much, then they exit. At the end of their loop, they find the optimal policy by essentially calculating the Q values and figuring out which is the best one. So it's a little bit like in what we did last class. We actually didn't do this first. First, we figured out just the values, which was this, the value function, using exactly the value iteration that we said before. But actually, if you know the values, then you can figure out the Q values. You can figure out the Q. If you know V, you can figure out Q. And that will tell you what is the best action to take anywhere. So all of this is a recap from last time. Okay. Any questions or comments about that? So today, what am I asking you to do? I'm asking you to do pencil and paper math. What would happen if you took the value iteration algorithm, which works for the real Bellman equation, and I want you to apply it to the baby Bellman equation. The baby Bellman equation is for where there's no actions, right? It's just a Markov chain. There's no maximum over A. You could imagine we're playing snakes and ladders where you don't get a choice. You just roll the dice again. That's the only thing you do. If there's only one action, it's the baby Bellman equation. Another way to say it is if you've pre-decided what your policy is going to be, then there is no choice on what you do, and you just follow the policy that somebody told you to follow. And then it's the baby Bellman equation. If you do this with pencil and paper, you're going to get some answer in terms of the reward vector R and the matrix M. M should not have a vector sign. M is a matrix. And the question is, the thing you get, have you seen it in the course before? And if you want to say what you got, you can describe it in this little text box. So I'll give you a couple minutes. Try to work out what happens if you do a bunch of iterations of value iteration on the baby Bellman equation, and tell me if you've seen it before and what you got. Okay, I'll set you loose for a few minutes. Do you think? And work. Okay, and the important equation, I guess, is the baby Bellman equation right there. Okay, there's like 30 seconds left. Who needs more time? Hands up for more time. Let me give another minute or so here. A few people are not in yet. Okay, there's like 10 seconds left. Put in what you have. I mean, I guess if you come up with something and you haven't seen it before, then put in no. Feel free to put like nothing in the description. If you're not confident about your description, that's okay. Okay. Okay, I'm going to stop it. Let me see what people got. Zoom out a little bit. Okay. What did people say? Have you seen it before? 13 people have seen it before. That is the correct answer. You should have seen it before. And what did you get? Let's see. 10. Okay. Well, I didn't tell you. Okay, anyway. Okay, it's kind of like the steady state solution. It's like the right kind of thing, but not quite. Some reward thing. All right. Look at this. This is a very nice explicit thing. This is the perfectly correct answer. So let's see what this is. So if you put in this, pay attention. We're gonna explain it. Okay. All right. Let's take a look. So we're working on this. This is the real Bellman equation. We are today, or for this warm-up, doing the baby Bellman equation, which is the same thing, but there's no actions, right? Or you could think of there's only one action you must take. You are forced to take one action. It's just R plus MVK. And we saw that this gives you the values, the long-term value of the reward, right? So the value function is the total return, all your rewards and prizes. Total return given S0 equals S, right? This is what we're looking for, and we're iterating it. We know it's supposed to satisfy this with V on both sides, and now we're iterating it. And I wanted to start with V of 0 equals 0 to see what you get. And let's just like do it by hand. So V of 0 is 0. Then what is V of 1? Well, the equation says it's R plus M times V of 0, right? You take what you had before, you multiply it by the matrix M. That moves you forward in time by one step. And then you add R. And now, this is the 0 vector. That's something I can calculate. M times the 0 vector is 0. This is 0. Equals 0. Okay, so this is just R. V1 is R. What is V2? It is same formula. You take what you had before, you multiply it by M, you add R. So you do R plus M times V1. But what is V1? V1 is R. So take this guy, V1 equals R, and put it in here, R. Okay, so it's R plus M times R. Fantastic. What is V3? V3 is R plus M times V2. You take what we had before, and you feed it into here. Okay, great. R plus M times R plus M times R. Okay. And now it's helpful to expand this multiplication M out and to collect things in a slightly different order. So if I read it like this, it would be R plus M squared R. But why don't we write it the other way around? R plus oh no, I guess that's fine. Okay, let's do it in the order that it came out in. Okay, great. M squared R. Okay, R plus M squared R. Hopefully you can start to see the pattern here, and at least one person did see it who typed it in. V4 is going to be R plus this whole thing times M. When you multiply this whole thing by M, all the exponents of M go up by 1. You're going to get MR plus M squared R plus M cubed R. And then V5 is going to be even one more. So take this whole thing, multiply it all by M. That's like shifting it over by 1. MR plus M squared R plus M cubed R plus M to the 4R. And I got that by taking all of the individual terms and multiplying them by M. So everything kind of adds 1 to the power of M. And at the end, I add R. Okay. And now you see this nice equation that we had before in the course. This is our very first formula for finding the total returns. We said the total returns, well, there's the rewards now, the rewards on the next step, the rewards on the step after that. You add them all up, and we did this for the very first example in snakes and ladders. This was our first formula to figure out how long it takes until snakes and ladders finishes. We set a reward vector of -1 at every single step. And if you add this all up, this is how many rewards you get up to time 5. If you were to keep doing it forever, you would get all the rewards you get ever. And that would tell you the expected amount of time until you finish Snakes and Ladders. So this is our formula. I think we wrote it like this. We wrote I plus m squared plus dot 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 plus m to the n all times r. Oh boy. Why does the computer hate me? Okay. This is what we wrote for Vn. And earlier in the course we said if you take the limit as n goes to infinity of Vn, you get the value vector V at any time. And a lot of people, this is how we did in lab 1. This is how we calculated the rewards. So what is the point of all this? Value iteration just recovers what we were already doing. And we said in that one, we said let's take a large enough n to make sure that we take enough steps to see everything. It's the same issue in value iteration. How many iterations should you do? Same exact kind of question. Okay. All right. Questions or comments about that? How many people had something like that on their page? Only a few people. Okay. So I'm glad we did it. Feel free to ask any questions if you have them. I suppose this is the closest to a linear algebra problem as we get in the course, right? So if you didn't like linear algebra and expanding matrices, then this was probably the same kind of issue. Questions or comments? All right. So what are we going to do in the rest of the class? We're going to keep doing value iteration. Last class, I sort of did it somewhat quickly for pig, which was, in pig, there were 2 actions, staying or rolling again. I'm going to show you a more complicated example, and I'll go through it slowly. We'll kind of like live code it together. I have the answers here in case we get lost, but we'll try to come up with it together. And we're going to do a problem where the actions you have are not just 2 actions, but you have many actions available to you at every step. And we're going to do a problem you've seen before, and one that's also in the textbook, and that is the gambler's problem. Let me show you what the textbook says about the gambler's problem. So here is the textbook gambler's problem. Can I hide the sidebar? There we go. Okay. So here is the gambler's problem. A gambler has the opportunity to make bets on an outcome of a sequence of coin flips. This is just like the gambler's problem you guys did in the last lab. If the coin comes up heads, he wins as many dollars as he has staked on the flip. If it's tails, he loses. So it's even odds for payouts, right? Whatever you bet, you either win or lose that amount. The game ends when the gambler wins by reaching his goal of $100 or loses by running out of money. So again, the gambler is going to keep playing until they reach a terminal state of their goal. In this case, they said it was $100, or 0. If you reach 0, you're done. If you reach $100, then you leave the casino and you're happy. On each flip, the gambler must decide what portion of his capital to stake in an integer number of dollars. So we're going to say you have to pick an integer number of dollars. And here is the sentence that is a big mouthful. This is what you guys kind of did in lab 1 already. We thought about this problem as a Markov chain with rewards there because I told you the betting amounts, right? So I gave you a vector that said the bet sizes. In this one, there is no vector that tells you the bet sizes. Your job is to come up with that. Your job is to select the optimal bet sizes. And that's what this sentence means. So this problem can be formulated as an undiscounted episodic finite MDP. What does this mean? So first of all, you have to know the acronym MDP. If you don't know the acronym MDP, you have no hope of understanding the sentence. MDP is a Markov decision process. So it's a Markov chain with rewards and with actions. That's what an MDP means. What do these other things mean? Undiscounted. This is a word that means the rewards in the future count the same as the rewards now. We had this parameter gamma that controlled that. And this is saying gamma equals 1. Let me write these down. I think these are worth doing. If you're reading the textbook and you need to translate what they're saying. So MDP is a Markov decision process, or process, depending on who you ask. There's no way that's how you spell process. Is that? Well, okay. Let's go with it. You can fix it in your note if you have an alternate spelling. Okay, that's what MDP is. Undiscounted. This means, let's put 3 equal signs. So this is like the definition. Means gamma equals 1, i.e. return is R0 plus R1 plus R2 plus dot dot dot. So sometimes you can discount future rewards, and this one is undiscounted. When you have something that goes on potentially forever, it's really important that you discount. Otherwise, you're going to get infinities that crop up. So if you have a robot and you're like, hey, robot, you're going to get $1 for the rest of eternity, then the robot it'll be like, wow, I'm going to be so rich. I'm going to be infinitely rich. So you have to discount its future values so that it like plays with finite numbers and makes the right choices. But this one, because it eventually ends, either you hit 100 or 0, it's going to end at some point, and that's why it's okay to make it undiscounted. What other words are there in here? Episodic means an episode is one kind of run. Episodic means it eventually ends. So instead of running forever, it has these episodes, and in each episode, you end up with an outcome, either getting to $100 or getting to 0. So this is another good vocabulary word. An episode. That's a one. Should I call it a run? I don't know. You gotta fill in the right word. Run of the chain. Eventually ends at some finite amount of time. Okay, so that's an episode, and episodic means it's made of episodes. It's not something that goes on forever. It ends at some finite amount of time. A good example of something that's not episodic, you can have a Markov decision process of, say, like balancing a pendulum or something. And in that situation, you just say, like, okay, you have to balance it forever. We're not going to stop at some point. There's no terminal state we're going for. This one has a terminal state. It's episodic. Okay. So we've unpackaged the vocabulary from the textbook. And here is what they told us. They told us the state space and the actions. So the state space is the gambler's capital, how many dollars they have, and they're using S between 1 and 99. If you get to 100, you're done. So they're just like, let's not include that in our states. We can include that as sort of an extra terminal state if we want to. That's going to be a state where you're stuck there forever. And S0 is the same thing. When you run out of money, you stay there. The actions are the stakes. So A is between 0 to the minimum of S and 100 minus S. This minimum of S and 100 minus S should remind you of lab 1. You can't bet more dollars than you have. You can't bet more than S. You should never bet more than it would take to reach the end. So that's the 100 minus S. And you can see this A actually depends on what S is, right? So the actions that are available at every state depend on how much money you have. If you have more money, you can bet more. If you have less money, you can't bet more. Okay, so that's the setup. This is so far exactly like the lab 1 problem, except for instead of just pre-telling you what the actions are, I'm asking you to find the optimal strategy. Here is a description of the rewards. The reward is 0 on all transitions except those on which the gambler reaches his goal state when it's +1. So in other words, the gambler gets a reward of +1 right when they finish. This is exactly what I was calling a prize. So I was saying it's a prize. You get to the end, you get a one-time prize of +1. I think they said it was a free car if you reach the end. In this book, they said, let's think of it as a reward when you're at the state right before you go to 100. You get a reward as you get there, right? And they're saying it's a reward. Every time you go into the state of being finished, we'll give you a new free car. Of course, you can only do that one time, because once you do that, you're stuck there forever. So I like to think of it as a prize. Of course, this distinction between prizes and rewards is entirely in your head. So it just depends on how you want to think about it. The point is, he's trying to get to the end. You get to trying to maximize that probability. Right, okay, so because he gets a reward of +1, the expected reward is the probability of getting to the end. That's something we talked about. Okay, let's keep reading. Yeah, the state value function, that's the value function V, that gives the probability of winning from each state, right? That's exactly what I just said. A policy is a mapping from the levels of capital to stakes. That's the bet function, right? You tell me S, I tell you how much to bet. And the optimal policy maximizes the probability of reaching the goal. Here's a parameter you've seen in lab 1. pH is the probability of winning each individual coin flip. And if pH is known, then the entire problem is known and can be solved by value iteration. That's what we're about to do. So we're going to implement this, and we're going to find the optimal strategy. Here they have given us in a picture of what our function is supposed to look like at the end. So here is the value function, and here is the optimal actions that it finds. And you can see it's quite a weird looking function. So if you just look at the optimal actions that it finds, it says if you're at $50, you should bet all 50 of your dollars. And you have a chance maybe you make it to the end. But if you're at $51, well, you only bet $1. There's kind of a there's no like pattern, right? So if you're at 50, you go for it. You're like, yeah, let's go. We're going all the way to 100. Here we go. And you either lose or win. If you're at 51, you're like, $1, please. I will take a small bet. And we'll see kind of what happens. We're going to do it in general. You can get some interesting things as you vary n, and you can get some interesting things as you vary the final parameter, the p heads. So I think here they use p heads equals 0.4 or something. Okay, so that's what we're about to do. Yeah, p heads equals 0.4, and the value function and the policy are here. So we're going to make a computer program that outputs this. Your lab next week will also have problems that are like this. There's going to be some problem. I'll explain it to you, and you will make a function that does this stuff. Questions or comments before we get started? Yeah.
Is it going to be one question or multiple questions?
I haven't really decided if I want to make multiple smaller ones or like one bigger one. Yeah, it'll be approximately the same length as the previous lab in total. Yeah.
Is the gambler, sorry, I didn't remember, is he always betting on heads, or is he just betting whatever he wants?
Oh, I think the way to think about it is that he's betting on something and he has p heads of winning.
Okay.
I called it p win, I think, when we did it last time. In this one, I guess they said heads is the winning thing. But yes, of course, see, this is the thing about casinos, right? If they have a coin that comes up 40% of the time on heads and 60% of the time on tails, they're not going to let you bet on tails.
Yeah.
So that's why I think it's better to think of, they're playing some weirdo casino game, and at the end you either win or lose, and you have some probability of winning. Okay, actually in casinos, normally they do let you bet on tails, but they have the odds different. So you don't get a full dollar when you get like half a dollar or something if you... Anyway, we don't want to think about that. Yeah. Question here.
Actually, now that I look at it, I understand. I was going to ask what the sweeps were, but...
Yes.
That's
So,
just the final.
well, see, yeah, this is great. So in value iteration, right, you start with some bad estimate, and then you improve it. That's what they're calling sweeps. So for them, a sweep is going through one round of value iteration, applying that equation once. Why do they call it a sweep? We're going to do it with matrix vector multiplication, but they do it state by state, and say that when we go through all the states, that's one sweep of all the states. Yeah, great question. All right, let's do it. So this will be some live coding, which maybe is very boring at times while we figure out syntax errors, but hopefully instructive. Okay, so blank thing was the very first thing you do. You got to import numpy as np, and because we want to make some plots, I'm going to import matplotlib.pyplot as plot. Hopefully this runs, otherwise we're in bad shape. Okay. Okay, here we are. So now what we got to do, we're going to set up the value function and the iteration. I'm going to, instead of making the final state 100, I could just type 100 everywhere. But let's call that n. That'll be the target, and that is 100 to match what they did. We're also going to have a p win, which is 0.4. If this was your lab, then n and p win would be inputs to the function, and you would write the function. Because I'm writing it as a block, we'll be able to follow along in the variable explorer what the value of everything is. That'll help us debug as we go. So I like to do it like this. If you want to convert it to a function, we'll do that at the end. Okay, so we got n and p win. I need the value function. I'm going to use math slang and just call that v. V is going to be the value function. The value function. Okay. What kind of object should the value function be? I will take suggestions. Yeah.
A vector?
A vector. Yes. How do you make a vector in NumPy? One way is to start it as all zeros, np.zeros, and then over here you put in the size of the vector you want. If you put in a tuple, then it'll make an array. If you put in just one number, it'll make a vector.
Good question about p when being set as 0.4. Is that just for trying to get a weighted thing? Or?
Why did I do p win equals 0.4? Because I want to match what these guys did, and they had p win equals 0.4. And so we're going to run it, and we're going to know that our program is working if it looks like this. Later, after we have it running, we can change it. Okay. Okay, so I got to put in the size of the thing. What is the size of the thing? you might think it is n. If you put an n, you will go straight to Python jail. Why will you go straight to Python jail? If you put an n, you have a vector that ends at n minus 1. Okay, and we don't want that. So you have to put an n plus 1, and that's because Python starts at 0. Value function n plus 1, since Python starts at 0. You might have noticed in lab 1, I gave you a lot of pre-made things, and I made sure to set it to 10 plus 1 for you. I probably won't do that in lab 2, so that you learn and have to do it. Don't screw up the indexing. Okay, so vi, or let's do v of s, represents the value at state s for s in 0 to 100 inclusive. And by making it n plus 1, it works. I guess 0 to n inclusive. Okay, so there's n plus 1 total states because we're including 0. I'm also going to initialize one entry here. So this started as all zeros, but that's not a great guess because there's a piece of information that I know for a fact that I can include right now in my estimate for v. And that is the value of v of n. What is v of n supposed to be? Yeah, I saw somebody mouth it. Yeah, what is it? 1. It's 1. Yeah, v of n is 1 because if you start at position n, if you're at position n, you've won the car. Congratulations. You get a value of 1. That's exactly what they told us in the problem, right? They said, when you reach the goal, it is plus 1. So the value of the other states, we don't know yet. We're going to have to figure out as we go. But the value at state n, I know. I might as well include that information. And that is the prize at 1. Okay. So you could do everything with v's just like we did originally. Right? So just like we did over here, you could work only with the v function. But it turns out it's kind of convenient to work with the q function. It's easier to plot things. It's easier to find what the optimal decisions are. So I'm going to keep track of the q functions as well, not just v. I'm going to do both. And this is like my philosophy going back to what we did last class of having 2 equations. Can I find what we did last class? It was this one. Okay. So I showed you the Bellman equations, and I said you should think of them as 2 equations. Where are they? Too big, too small? Okay, yeah. Okay, yeah, here. So I said we should think of them as 2 equations. V star is the maximum of the q's, and q is related to the v's. And that way, you don't need to like eliminate one of them. You just have the q's and the v's together. I will say, if you're working on a very big problem and you're like out of memory on your computer, then you can just get away with just one of v or q. You pick. V is the smallest thing you can do. So if it doesn't fit in your computer, just use v. But I'm going to do v's and q's so that I can use both equations and not have to eliminate one of them. So I'm going to do the q's. So let's go to where we're working. Untitled 94 q. This is going to be the q functions. Okay. What type of object is q? Yeah.
Matrix?
It's a matrix. So you might think it's a vector. It is not a vector because we're doing q of s comma a. It sort of has 2 inputs. So you can think about it as a matrix or something with 2 inputs, one for what state you're in, one with what action you're taking. All right, so it's going to be a matrix. How do you make a matrix? Again, you can use np.zeros, but now you're going to put in the axes a and b as a little tuple here, and I'm going to do n plus 1, because I want the states, the s, that's the same thing as before, 0 to n plus 1. I'm putting in the actions a as 0 to n plus 1, but that is not quite right. So in NumPy, you have to make a matrix. You can't make a weird piece of a triangle. So right now, s is between 0 and 100, and a is between 0 and 100. Okay, but now I'm going to try to put in the rule over here that it told me that, so far a is between 0 and 100, but that's not quite right. A is supposed to be between 0 and the minimum of s and 100 minus s. How will I include this information in my program? Well, it's actually quite tricky to do that in NumPy exactly. So if you want to make a NumPy array that really only goes up to s times 100 minus s, then you're in trouble. But I'm going to have a little workaround because I know what these things represent in real life. And Q is going to be the value function. It's going to tell you how much value there is by choosing something. What I'm going to do is I'm going to allow the computer to pick things that are higher than the actual allowed value, and I'm just going to give it a horrible value. And then the computer will never pick that, okay? So that's my goal. That's how I'm going to do it. So what I'm going to do is I'm going to, here is like a hack. Oh yeah, this is what the kids call hacks. Hack. Make the computer never choose an action larger than allowed. What I'm going to do is I'm going to make Q of s comma a, I'm going to make it 0 if a is bigger than the minimum of s and n minus s. So that's what I want to do. I'm going to say you get no value at all. And actually, to be extra careful and to make debugging later, let's say you get -1. Okay? So if you choose a value that's not allowed, you're at the casino and you're betting. Of course, if you win the prize car, you get +1. If you lose, you get 0, you leave. But if you make a value, if you try to bet something that's illegal, the casino will take your car out of the parking lot and leave with it. Or you get -1 prize car. So never ever do that. Technically allowed, please don't do it. So how am I going to do that? Let's just do a simple for loop. For s in range n+1, and we'll make for a in range n+1, and I'll call it this the min bet. The min bet is the minimum of s and n minus s. That's the minimum you have to bet. And let's say if a is less than min bet, then this. So this is like a very simple way to program this. These kinds of for loops, if n is a big number, can be very slow, and there's better ways to do this. You can do it with np.indices and things like that. But in the interest of not having bugs while I'm live coding, let's do it the simple way. Okay, let's see if this works. So, what do I have after running all this? You can see in the variable explorer over here, I have an array of shape 101. That's a vector. V is all zeros and a 1 at the end. That's great. And then Q is, what is Q? It's an array, mostly zeros and some -1s where you're not allowed to choose those actions. Okay, so far everything is set up. Now we just got to put in the value iteration formula, and things will work out. Questions or comments so far? Yeah.
Why do you need to do the second part instead of using like a jagged array or something?
Yeah, so you could use a jagged array or something like that, but it's kind of complicated, and you have to go read in the documentation. So this way it's like a hack to make it work with a square array by just like forbidding part of the array through math, rather than like forbidding part of the array through computer science and like reading the docs. Yeah, that's why it's a hack. Yeah.
Should it be greater than instead of less than?
Yes, that's very good. Yeah. All right. Amazing. Wait. Okay. Yeah. This is not the min bet. This is the max bet. Okay. Great. Max bet. If you're greater than the max bet, then you go to jail. Not less than. Okay. And actually, let's also forbid a equals 0. Let's forbid a equals 0. Because I don't want you betting $0. If you're allowed to bet $0, we can get into a loop where you just like never move, right? You just like decide I'm not going to bet any money. So let's also forbid that. Okay, great. So now we're going to just put in, basically, all we got to do is put in the value iteration formula, the Bellman equation. The Bellman equation, and we're going to update it as a value iteration. And let's peek at what the Bellman equation is. The first part of the Bellman equation says V equals the maximum of the Q's. Very nice. So I'm going to enter this as an equation. You could do it like this. V of s equals the maximum. This is a treacherous spot where you can easily make a mistake. And that's because there's a function called max, and there's a function called maximum, and one of them is the wrong one. Okay, so if you choose the wrong one, nothing will work, and you'll be like, I put it in correctly. It says maximum. Like, it's all working. Let's have a vote. Who thinks max is correct? Who thinks maximum is correct? Who thinks max is correct? All right, who thinks maximum is correct? So maximum is wrong. If you put in maximum, you lose. And the way you know, you can go read the documentation. But the way you know is by what they input. So maximum inputs just one thing, which is some array A, and the little hinter, if I put in an open bracket, will give me a hint. So you input just an array, A. If you type in maximum, what will it say? It will say, okay, tell me about maximum, please. Maximum, so here it's saying x1, x2. So if you put in max, you just have one thing you input. If you put in maximum, you have two things you input. What does that tell you? Well, maximum is actually doing comparing two arrays and tell me the maximum. So it's like I have two things, tell me which one is bigger in each entry, and output something of the same size. It's doing a bunch of comparisons. Whereas max, if you read the documentation, is doing the maximum of an array along an axis. So that's the one we want. We want the maximum. And we want the maximum of the Q's. So you could put it like this. So one way to do it is you could do this. And this would say, this colon means give me the whole vector at S of all the possible actions and find the maximum value amongst all the possible actions. This is one way to do it. Yeah, why don't we just do it like this? Let's do it like this. For S in range n plus 1, please find the maximum. And this little colon thing, if you haven't seen it before, is going through all the things and returning the maximum value. Okay, so that's one part of the equation. And then the other part is the Q's. So there you go. V equals the maximum of this. And the other part is this part. Q is M times V. So Q, what you do is you get the reward you get now, plus you get the rewards you get from the state you end up in. That's the next part of the equation. So this is Q of S comma A. And the answer is going to be the matrix MA. So you choose the action A. That tells you something applied to V. OK. Of course, we don't have a matrix A. But we know what the matrix does. It's supposed to say, what probability do you go to where? So because in this problem, we know what's going on, I can just kind of like replicate. I don't need to. I could write out a whole matrix A. It would just take us a little bit of extra time. Instead, I'm going to write it out with probabilities. So what it's going to be with some probability P win, something happens, something. And then with probability 1 minus P win, something else happens. OK. And what are the things? Well, if you win, you go up by A, right? You chose to bet A, and you won. So with probability P win, you move to state S plus A. And what I specifically want is the value there. So the value at state S plus A. And over here, if you lose, then you move to the state S minus A. And this works. This is perfectly correct. And I think this is like really encapsulates the Bellman equation. What is the value of being at state S and choosing action A? Well, you're going to get the value at S plus A or the value at S minus A mixed together with the probabilities of those things happening. You also get some rewards, right? R. But the way I have this set up, you only get a reward at the end. I'm thinking of it as a prize, so the rewards are 0 in this case. So this perhaps is the most complicated math line in the whole program. But if you understand it, then I think you know all the math. OK. A couple things to make this actually work. We're looping over all the S's. I need to do this for every A. So let's do for every A, for A in range n plus 1. And again, let's forbid all the non-allowed bets. If you allow non-allowed bets, you're going to get an overflow here. Either S plus A or S minus A will leave. So the max bet is the minimum of S and n minus S. And we're only going to do this if A is allowed. So A is less than the max bet. I guess less than or equal to the max bet. Then you can do this. OK. So there's Q. OK. And this loop will do a thing. OK, it'll do a thing. Let's run it and see if we get a bug. All right, it worked. Amazing. What are the odds? OK, we did it. We solved it, right? The equation says V equals this and Q equals this. We're done. Except there is a problem. And this can happen sometimes. When you read these equations on the paper, that V is the maximum of things, and Q is something, And then you go and you put it on your computer, you put the equations down. It turns out equals means different things. So on paper, the equal sign is like, we want this thing to be equal to that thing. On the computer, it's setting, right? We're setting v equal to this thing. Have we solved the Bellman equation? No, we haven't. We've just set v to be the maximum of the q's, set q to be something in terms of the v's, and then we stopped. We haven't solved the Bellman equation. We haven't even written down the Bellman equation. What we've actually done is we've done one iteration of value iteration, right? We just did whatever it was before, we've updated it to the next thing. If we want this to be an actual good program, we need to iterate some number of times. So we're going to do, this is iterated once, and to fix it, I'm going to do for iters in num iters. You could also do that thing with the delta and keep track of how much v is changing. If v barely changes from one iteration to the next iteration, then you know it's a good time to stop. But let's start with 10 iterations, and we're going to iterate it 10 times, and just do that over and over again. And you see that as you go, the v's and the q's will update. And to make sure I see what's going on, I can plot them. Plotting, this is one life pro tip. I would never write plotting script from scratch. Always go and copy paste someone else's plot, and then modify it to be what you need. Because there's all these like stupid things like where do you put the colors, where do you put the line style. So I'm going to copy and paste it. This advice is out of date. Okay, go ask. Let's go ask ChatGPT. This will be fun. ChatGPT. Let me see if this works. This feels illegal. Okay, but this is I guess the world we're in. Let's ask ChatGPT. Okay. Can I? Okay. Where did it go? Okay, hold on. Stand by. I've put ChatGPT in jail or something. We need to bring it back. Okay, yeah. Okay, I see where it went. Okay. Can I do this? All right. ChatGPT. Okay. Okay. All right. I'm plotting some stuff in matplotlib in Python. There's a value function v and some, let's just say, how do I plot it? Which is a vector size n. How do I plot it? All right. Okay, we did that. Okay, nice example. Plot vector. Okay, so I made this function, which is plot vector. And really what it's doing is this line. This is line we need. So in this case, I think if you know what to look for, it gave us a lot of stuff. You can copy paste it in. Let's do it. Okay. So this is what we want. So we're going to plot inside the iteration so we can plot as we go. And we're going to modify what ChatGPT did. Okay, so n we already know, right? We already know what n is. X is the range of n. We're going to need that in the plot. So that's actually helpful. And again, it's n plus 1. So ChatGPT screwed up. Okay. Of course, how is it supposed to know? Anyway, okay. So this will plot the value functions. The x label is our states. And the y label is the value. Thank you, ChatGPT. Okay. And this is the plot of the value function. Okay, and it's going to do a grid, and it's going to show it. Okay, let's run it and see. Int object. What is it not like? Of course, this is the classic mistake. You cannot iterate over in 10. You have to iterate over 10 things. All right. Okay, value function. One thing. Let's add one little thing here, which is to the title. We'll not just say plot of the value function. Let's say at iteration, and this is a good pro tip. Iter, if you put it in curly brackets, and you also put an f at the beginning, that is called an f string, and the computer will put in what iteration we're in every title. Okay, let's see if this is working. Okay. Oh no. for iters. Let's try again. Okay. All right. So the value function it thinks is -1 in a bunch of spots. Oh, somehow it got to -1. Okay, let me. So I think that thing I did before when I made this -1, something went slightly wrong. Let's see if we can figure out what it's doing. All right, let's just make and see what it does. Okay, so things are not working. We have a bug, and the way I know we have a bug is it thinks the value of the state 100 is 0. Right? So somehow it got overridden into thinking that the value of state 100 is 0. And I told it the value of state 100 is 1 at the beginning. So what is it doing? Obviously, at some point in my code, I updated the value of 0, and something went wrong. I think I know where it is. Okay. This is great. See if you can spot which line the bug is in. It's in the 20s. There's one simple thing we can fix. I think that will fix everything. I'll give you guys a yeah.
Is it 26? You can add another condition where S is not 100?
Oh, yeah, okay. This is one way to do it. So one way we could do it is in line 26. So first of all, I also wanted to forbid bets of 0, right? So why don't we put that in as well? So we'll put in and A not equal 0. That's one valid thing. You're saying we should also forbid
betting when
and
we
S
have 100.
not equal 100. I guess N. That would fix it. Another thing you could do is I was thinking, that's totally right. Another thing you could do is you could tell it only go up to N. Don't go up to N plus 1, and then it will just never update the last state. So because I already know the value in the last state, I could do that. If you just put it here, it's still going to update this one. So you would need to forbid it over here. You would need to have an if S not equal N. You would need it to go right there. But so I think if you're going to put it there, let's put it over here. And we're going to just do it in here. So I'm going to modify the range. Instead of being N plus 1, it's just N. And I also probably shouldn't update state 0. At state 0, the value really is 0. So why don't I go from 1 to N? And I'll leave myself a little comment. Only update states 1 to N minus 1, where value function is unknown. So we know the value at 0 and at N by going range 1 to N. Sometimes in my code, I will write things like this to remind myself. N is actually N minus 1 plus 1, right? So this only goes up to N minus 1. That way, I only update states where the value function is unknown. I don't need to update the states where the value function is known. In fact, I'm getting a bug because I did. So let's do that. We'll put this thing back to -1. That actually was helpful in identifying the bug. Okay, and now let's take a look at our plots. Actually, okay, here's a question. Here's a question for ChatGPT. How do we make the line thicker? How do I make the line thicker, please? What does it say? Line width. Okay, amazing. Yeah, this is actually, for plotting things, ChatGPT is truly next level. Okay, we're here. Let's make the line a little thicker so you guys can see it. All right, there we go. Okay. So, can I zoom out? All right, so here we go. Iteration 0, iteration 1, iteration 2, and so on. And they're starting to look more and more thing. We get this kind of thing. Let's compare it to the textbook answer. Looking pretty good. That kind of thing. So it looks like our code is more or less working. Let's see if we can make it plot this. So for this one, we have to figure out the optimal actions. So far we have the optimal value function. How do we get the optimal actions? This was the last Mathmatize question of Tuesday's class. Does anyone remember the answer? How do you get the things? Or I guess more importantly, how do you convince the computer to tell you the optimal actions? Let me make a little line here. And what I could do, I'll put it, we're looping here. Let's make an optimal action of S Oh, this has a name. This is called policy, right? The policy we're finding out. Let's figure that out. The policy of S, and it's what? How am I going to get it? So first of all, policy has to be a vector. It's the same kind of shape as V. So let's make policy over here. Policy is going to also be np dot zeros of n plus 1. Actually, why don't we start it as ones? You always bet 1 to start with, I guess. But how do you get the policy from everything we have? What do you do? Yeah.
Is the max of each Q value at, I guess, axis equals 0?
If I was a computer and you said to me it's the maximum of each Q value, then I would say, no, that's wrong. That's the value function, V. If I was a human, I would say, yeah, that's exactly right. The index of the max. So it's not the max, it's where does the max occur. It's the argmax. And in fact, really what we're doing, right? V is the maximum Q value, right? What is the maximum value you can get? The policy is where does the maximum occur? Which action should you take to achieve the maximum? So I believe it should be np dot argmax of Q of S, comma, colon. All right, that worked. Okay, I'm going to do one other silly thing. You definitely don't need to do this. This will work. Everything will be fine. If you run it like this, it's going to take which value is the largest. That's what we want. Very good. The problem is sometimes there will be ties. So betting $1 and betting $2 will have the same value. And for humans, you'd be like, okay, great. They're tied. But in the computer, it only stores things to so many decimal places. And so even if two things are tied, they're both 0.333 repeating, one of them will look larger to the computer. And so argmax will do weird things to break the ties. I don't want it to do weird things to break the ties. I would like it to break the ties in a predictable way. So I'm going to do a little like ninja jujitsu, another hack, okay? I'm going to subtract off 0.00001 times np.arange n plus 1. And so what I've done is I have subtracted off a tiny little bit from each entry based on how big it is. The bigger entries get more subtracted, the lower entries get less subtracted. And that way when there's a tie, it will pick the smaller bet size. So this breaks ties so smaller bet sizes win. Are chosen. Okay? So it's a little hack, but that should give us the policy. Okay, and if I run it, let's check that policy is appearing in our Explorer and is doing the right kind of thing. There's the policy. And I suppose we are doing a bar chart. So let's ask ChatGPT, how do you do a bar chart? How do I do a bar chart? Okay, so ChatGPT very helpfully says bar of x v. So let's do a little bar chart with our policy and see if it works. Plot x comma policy. Okay, not plot bar, because that's what ChatGPT said. Okay, and let's see what this looks like. Ooh, okay, very nice. All right. Okay, so here's iteration 0, always bet 1. Here's iteration 1, bet 50. Here's iteration 2, more bet 50. Oh, this is cool. This is doing some weird stuff. Okay, so this is looking pretty good, exciting. There is one thing that bothers me. Where did the value function go? Right? Before it was plotting the value function, and then I was like, please add on the bar chart. And now there is no value function. Where did the value function go? What happened to it? Yeah.
Did you overwrite it with the bar function?
I did not overwrite it. It's on the same plot. Because if you plot two things, it'll plot them on the same plot. That's not the issue. Yeah.
Are the axes like super weird?
The axes are super weird. Yeah. Do you remember the value function is a number between 0 and 1. So here it's like bet 50, make the axes go up to 50. So where is the value function? It's hiding right here. Okay. The value function is in the first like micrometer over here. So how are we going to fix this? There are a few different ways you could decide, but I'm going to do something a little silly. I'm going to take the value function, I'm going to multiply it by n. And that way the maximum value will, instead of being 1, will be n, and then it'll be on the same scale. Okay, and as to help me make sure I remember that, here's another really good pro tip. You can add labels to your things. So if you put in label, I'll say value function times n. That way it'll remind me it's the value function but rescaled to go up to 100 instead of to 1. And similarly for the bar chart, I will add a label. Let's call this optimal bet size. Okay. And I think by default the color here is blue. Let's make this one a different color. Let's make this color red. Red is R. Okay. So let's run this and see. Okay. Now we have a nice clear plot of what's going on. So iteration 0 thinks all the optimal bets are bet 1, and it thinks the value is 0 everywhere and 1 at the end. Iteration 1, nice staircase function. It thinks if you started at 50 or higher, you have a 40% chance of winning. And you can get that by, look, we're doing this maximum bet. We're betting to get to 100%, right? So we're kind of going all in. If you have more than $50, you go all in and hope you win. You have a 40% chance of winning. Of course, you can do a little bit better than that. How can you do a little bit better than that? Don't quite go all in. Try, if you're close to the end, go all in. But if before that, try to get close to the end. So we get this like staircase function, and it repeats. Then something really exciting happens. Now it's split up into 2 things. Oh, okay, wait. It occurs to me that everything is sort of off by 1, right? This thing has this split here. But you don't see the split in the bet size until here, right? What's going on? Let's go look at my code. When am I plotting things? This is a good life lesson. So here, I calculate V, and then I calculate the policy S, and only then do I update the Qs. So the policy is chosen from the Qs, but the Qs aren't updated till here. So I think if I put things in the opposite order, it will make more sense. Because policy, yeah, let's put this after. I think that'll make more sense. Let's do that. Then I think my storytelling will fit the plot a little better. Okay. Oh, you have to restart everything because, wait, I did restart. Okay. Do I have this in the wrong loop? Okay, I liked it better the way it was before. Let's go with that. When I did this at home, I did it with vectors. And so I think it was doing some things all at the same time that I'm now looping over. So I'm getting some interesting stuff. Oh no, have I ruined it? Yeah, you have to put this in the loop. Okay, maybe I did have that in the wrong spot then. Okay. All right. Okay, let's just leave it the way it was. It might be sort of like off by 1, but it's doing this kind of thing. You get this staircase function by having bets that bring you up to the next level of the staircase, and you end up with this very cool looking thing of having at 50 you go all in, at the other ones you don't go all in, and you can see it looks slightly different than what was in the textbook. So in the textbook, they came up with this thing. Why is theirs a little different than ours? It's because I put in that hack to always pick the smallest number. And in fact, if you read carefully, they say there's a whole family of optimal policies, all corresponding to ties for the argmax function. Can you guess what the entire family looks like? And there's actually a really interesting fractal structure that's going on here. You can see it if you put in powers of 2. So if you put in n is a power of 2, you'll see something nice. Let's put in n equals 128. You'll see a really nice thing happen, hopefully. So it kind of is fractals all the way down. If you put in a number that does not have a lot of multiples of 2, you'll see a different kind of pattern. Let me put in n is 129. So changing what we're going for by 1. Okay, I guess it didn't change it. Maybe I have screwed something up somewhere. Let's try 131. That's more prime. Okay. All right. Well, I guess it's always finding the minimum. Maybe I went too hard with the with this 0.001 thing. Let's do this and see what it finds. Okay. This is kind of more what I expected. You'll see, actually, for a lot of numbers, doing the all-in bet all the time is the best action. And you can kind of see shadows of that here. So it has this little region where it's doing the all-in bet. It turns out that can also be optimal. Okay. Where are we here? Okay, I think we got it working. We did what the textbook said. We did a nice example. That should hopefully give you some hints for the lab next week. So next week we're going to do something involving this. Next week we're going to learn about something different. What are we going to learn about? Something that's not value iteration. I'm going to ask you what's wrong with value iteration in a second. But are there any questions or comments before we move on to that next thing? Yeah.
Will this the code be posted?
I'll post it. Yeah. And in fact, I'll post the better version that I made before. Right. Okay. So here is the question for you guys. So far we've solved the one-player version of Pig. We solved the gamblers problem, and it works by iterating the Bellman equation over and over. Why can't we just do this always? Why can't you? What would be a situation where you can't just use the value iteration algorithm? It works very well when it works, but there are many possible answers for what the limitations are. It doesn't always work because blank. So think about really like what were the ingredients that we needed to get this thing to work, and when would it not work in practice? Okay, I'll give you a minute to think, and then we'll take this thing up. Okay, a few seconds left to tell me what you think about the limitations. I'm going to show you the code that I had prepared, and I'll show you what I did slightly differently than the way it came out in class. The way we did it is perfectly fine, but let me show you how I did it before and what is different, and how things come out a little bit differently there. And what I did is the only difference is I have split up. I have two for loops now. So I go over all the S values and I update Q, and then I go over all the S values and I update V. So in the code we wrote in class, we were doing these all together in one loop. And that kind of changes which values have had how many iterations, right? So when the Q values are getting updates, they're looking at the V values. And like V S minus A will have updated, but V S plus A will not have updated yet because it comes later in the loop. So by doing it this way, you can be sure that the Q values, they have the latest possible Vs, and the Vs have the latest possible Qs, and everything is working. So this is why they called, in the textbook, they call this a sweep. And so I guess what I'm doing is I'm being careful to sweep all the Qs first and then sweep all the Vs first. The way I wrote it in class, I was doing both at the same time. I think they both will work. This way is a little more clear as to how things work, and I think it will converge a little bit faster. Here's what happens when you run it with n equals 129, which is what I thought would be a cool reveal before. So it starts out like before, you do a max bet, and then you end up with these splits. It goes all the way down to the fractal bit of having these weird spikes at 50, where you bet all your money at 50, and you bet none of your money at 0. But then something really exciting happens. So here it's like fully fractaled out. 50 has a full bet, you have these things where you go, you want to try to either get to, when you're at 75, you either try to go to 50 or to 100. But then something really weird happens. This whole thing just gets filled in. It says, wait a second, we can do slightly better by doing the max bet always over here. And wait a second, we can do slightly better by doing the max bet all the way over here. And wait a second, we can do better by doing the max bet over here. And eventually, it finds after some iterations that the optimal strategy is always go all in. Always bet the maximum of what you have. If you have less than halfway, you're betting everything you have. If you are more than halfway, you bet enough to get to the end, and that is the optimal thing. So if you're doing a prime number, it turns out this is the right thing to do. If you're doing something with powers of 2, you'll see a number of spikes with the number of powers of 2. So if you do like 4 times 129, you should end up with 4 little spikes. I might have put in a big number and melted the computer. Okay, let's see what it does. So you can see it's going a little bit slow because my code's not great. But do I have 4 little spikes appearing? That would make me very happy. Okay, remember, it's going to like break down and then fill in. Okay, so it's broken it down. Is it going to start to fill? Oh, okay, here we go. Okay, so it has to do with the largest power of 2 in the prime factorization of the thing. Yeah?
Does that break down? Is that because P is less than 50%?
It's because P is less than 50%. So when you go to a casino and you're trying to reach the end, you want to kind of minimize the number of bets you make. Because the more bets you make, the more time the casino has to screw you over. I guess that's another thing we can try here.
So what if you put it at like 51?
Yeah, let's put it at, I'll show you what happens if you let's put in a reasonable number, like 100, and let's put in 55%. So this is not a real life casino. Don't go to the casino and bet thinking that you'll win money. So at a casino where P is 55, let's see what it eventually finds. So you can see, first of all, the curve is the other way. The curve before had all these like fractal things. This one looks like this. Okay, this is iteration 8, 9, 10, 11, 12, 13, 14. Okay, I think I didn't run enough iterations. You gotta run more iterations. If it's maybe make it 60, it'll make it no more. But let's num iters. Let's do 40. And again, you can check if things are not changing over time on the fly, but it's a little more annoying to code. I believe it should go down all the way to 1. So they kind of like the bet sizes will just like decrease until it figures out like, wait a second, I can just do better by betting smaller and smaller amounts. And then eventually it'll figure out, oh, you should just like do the minimum bet size always. And that's the best. So you can see the value function is going up as we go. The more iterations you do, it's finding more value by doing smaller and smaller bets. Again, 40 is not enough. I guess I need like 100. Let's okay, let's do 400. How about that, Mr. Computer? Well, we'll get this nice animation playing in the background. Okay. All right. So what did I want to say? Oh, yeah. Okay. So what's the moral of the story? Let me draw a little picture for you while this thing is running. One way to think about the policy, the thing we're doing, is we have the value function v, and then we have the policy, pi. And the policy function really was, in our code, was actually expressed through the q values. Expressed through q. So in our code, we actually had q, and then we were computing the policy by doing the maximum of q. That has a name. That is called the greedy policy. So we were doing pi, which is the maximum. So that the action you take at state s, we said is the maximum, and actually the computers will throw you in jail if you say maximum. You got to say the argmax of q of s a over a. So and this is called the greedy policy. It's called greedy because it just does the highest thing. We'll see later in the course why greedy is not always good. So you might think, oh, it's just the maximum. That's not greedy, but you'll see why it's greedy later. And we were kind of iterating. We were figuring out the value function and using that to figure out the q's, right? That was one equation. And then we were using the q's to figure out the value function. So we had the cycle of the 2 parts of the Bellman equation that went back and forth like this. So one is v is the maximum of the q's. And then the other one is that q equals m times v. And we kind of alternated these two things. in the code that I actually just showed you now that I wrote before, I was making sure to do them separately. In the code we wrote in class, we had a loop that was like doing both of them together. But this kind of thing in general has a name. It's called generalized policy improvement. Generalized policy improvement. And the textbook has some nice pictures about this. Maybe I'll show you them next class in the interest of time. But improvement. Let me show you some quick pictures, and then I won't explain the pictures, but I'll just maybe get you excited enough you'll go read the textbook yourself. Where is it? Show me the cool pictures. Okay, here it is. Yeah, so here is the picture that I essentially drew. We got pi and v. Pi is the greedy version of v. You got the value function v. They go back and forth, and then they draw this picture. They kind of say, like, you can think of what we're doing as we have a value function v and a policy pi, and we're kind of like, first we evaluate the policy, then we do the greedy thing, then we evaluate the policy, then we do the greedy thing. And you go back and forth, and you sort of like slowly converge towards the optimal value function and the optimal pi. And you saw that in the animation, right? As this thing was going, the value function is getting better and better, and it's finding better and better policies, right? So it's slowly improving the policies as it's getting more and more value functions. It's learning that, hey, wait a second, I shouldn't do these bets of size 10. The smaller bets are better. It's slowly improving and getting better and better. It's going to be really close here if it finishes and finds a value of the optimal action of 1 by iteration 400. So that's going to be pretty exciting. Let's see if it actually does. But so hopefully you can see from this like picture / animation, hey, it did it. Okay, that it's doing this back and forth like in the textbook. So this is like a common theme in reinforcement learning. Okay, let's see what you guys said on the Mathmatize question, and that's where we're going to start off next class. Limitations of value iteration. It doesn't always work because why? Time complexity. This is something that happens. So it can sort of get too big. If the state space is too big, things will slow down a lot, and you'll see it doesn't work. Infinite episodes. So episodes that go forever, what I would call an infinite episode, you must have a discount factor for it to make sense, and then value iteration is still totally fine. You'll just have a gamma inside the Bellman equation. Big depth and sparse rewards. Chess, I wouldn't say it's the problem with big depth. I would say the state space is way too big. And we're going to find out that's kind of what's going on in the first one. The value iteration formula, you kind of need to know what happens at every state, and you kind of need to iterate over all possible states. If you have like 10 to the 1,000 states, there's no way that's going to happen. And what's going on in it, so something like chess. Chess has way too many possible chess games to study them all. But the chess games that matter, the ones that like humans play, is much smaller. So value iteration goes over all the states. You want to have some smart things that look at the states that actually matter more than all possible states. And value iteration doesn't do that. So something like chess is a great example to see why value iteration doesn't work in chess. And we're going to work on things that work better in these large things. Okay, yeah. Oh, this is a great one. State action space, too large. That's a great reason. There's a couple other reasons. We'll go over them next class, and we're going to start learning some more methods that are more complicated. Question here, yeah?
What about if there's incomplete information?
Yes, this is the other big reason is that for value iteration, you need to know what happens everywhere. In real life, you'll see there's some situations where you want to solve it even if you don't know. Okay. All right. Okay, see you guys on Tuesday, and I'll post the things we worked on.
Yeah.